Thank you very much. So what I'm going to talk about is a technique that we developed. Guido Risaliti and I have been working on this forehand since 2015 now. We improve it, but before going into the results and the main point of this talk, I would like to introduce the technique first. So this is my introductory slide for those who have never heard about this, how to use quasars for cosmological purposes, so through what is called the Lx-Luv relation. This is my introductory slide, but I'm going to get you through. So let's start with the actual empirical relation that we use in order to standardize the quasar emission. And I often make the parallels with type 1a supernova, for which people are more used to. So here is one of the most recent compilation of quasars we published. Actually, the most recent. We are working on a new sample right now of 2,400 quasars selected from Sloan. Different colors are coming from different subsamples that we gather. And what you see here is a relation between the X-ray luminosity observed in quasar, the intrinsic X-ray luminosity observed in quasar at 2 keV, as a function of the UV luminosity at 2,500 angstrom. Now, this relation, log-log, has a slope of 0.6, so the relation is non-linear. And this is one of the main key points of this relation. The relation is non-linear, the slope is 0.6, and has an observed dispersion that is actually quite tight. This relation, I should point out, that is not new. It is known since the 80s, but back then the dispersion that was observed in the relation was much higher, 0.4 dex. What we have been doing is to understand the physics behind this relation. So we started from a completely different reason here. We wanted to understand whether the dispersion of the relation that we observe here, that is linked to the physics of quasars, it is actually intrinsic or it can be narrowed down. So this is actually the case. So 0.2 dex is one of the tightest relations that you will observe in quasar, and knowing that quasar are variable sources, this is actually remarkable. So we use this relation, and from the time being, so that's right. So in order to get this relation, we need to observe two quantities, as I said, the UV and the X-ray emission. And how do we select quasars? So if you look at the Sloan Digital Sky Survey quasar sample, there are 750,000 quasars. So then we end up with a few thousand quasars, right? So what we are looking at, in order to sample the intrinsic relation that we observe in quasar, is to look for the UV emission and the X-ray emission that is intrinsic to the quasar itself. Meaning that I select those quasars that do not show contamination from, for instance, like strong outflows, like what they are called the broad absorption like quasars are removed, or strong radio sources, or for instance, sources that have been absorbed both at the UV or X-ray energies. So what we are looking at are quasars that are actually happily accreting, and the main data that you will need are power loss, beautifully boring power source in X-rays, nothing that has weird features, and nice power loss in the optical UV. This is one of the examples of the spectra of redshift quasars that are actually within the sample that I have shown. So this relation is linked to physics, and there is a separate talk that I can do on that. So I'm going to focus on the cosmology, so the cosmological meaning of that. So having that being said, we can forget about luminosity from the time being. So luminosity has a cosmology plugged in, so we actually get rid of the cosmology, we work with fluxes, and by doing just simple math, you can get the luminosity distance, but just a function of just observables, okay? The UV flux, the X-ray flux, the slope of the relation, and its intercept. So the FX-FUV relation, it is, provides you with an independent measurement of quasar distances. Now, what we can do is to use this relation in a similar fashion as type 1a supernovae, and so we can build a Hubble diagram, as you can see here. This is the distance modulus as a function of redshift. This is the different colors correspond to the sample of quasar that I showed you before. The magenta points that you see here is the type 1a supernova. This is the Pantheon sample, and the residuals are shown at the bottom. There are two main things that I want to highlight here before discussing the results. The first one, it is striking that quasars have much higher dispersion compared to type 1a supernovae, and I mean, this cannot be hidden. But the power of the technique is that we can sample much larger redshift with quasars. So it's the combination of quasars and type 1a supernovae that makes the technique really powerful. This is the first point. Regarding the dispersion, we are working on making narrower, and this is something related to the quasar physics, but this is already a quite good sample that we can improve, of course. So now what you see here is the black points are shown here just for visualization purposes, and these are averages of the quasars distance moduli as a function of redshift. The dashed line is the flat lambda CDM model of type 1a supernovae and quasars fitted below redshift 1.5 and extrapolated at higher redshifts, while the red line is the fit of both quasars and type 1a supernovae across the entire redshift range using a cosmographic approach. Now, I'm not going to go into the details of the cosmographic technique here, but the point that I want to highlight, since we're talking about discrepancies, is that there is a deviation. We do observe this deviation that happens to be a high redshift, so started to be significant at high redshift, and the statistical significance of that deviation is between 3 to 4 sigma. Not super high, but still something that we stumble upon. So now, the first thing that we did was to, well, let's see what this deviation implies. So we started to fit more cosmological models. So we started to study different cosmological models, so fitting the data using, for instance, this parameterization, with this very well-known parameterization of the equation of state of dark energy, and supernovae plus quasars are shown here in blue compared to other probes, BAO, and the combination of all the three probes. Here is WA, W0, and WA omega matter. And as you can see, the combination of quasar and type 1a supernovae are pointing towards a negative W0, much negative, more negative than -1, and a slightly high omega matter value. Now, what is implied physically, this is an evolved dark energy density and a phantom behavior of quasar in type 1a supernovae. Now, the question is, do I believe that this is actually what happens? Absolutely not. This is because I'm assuming this model, and this is why I'm getting the result. So we try to, this was back in 2022, so we try to investigate this even further, and we extending the models, like for instance, using the interactive dark sector. This is a work that has been accepted recently. You won't find it on Arxiv. You will find it soon, but it's not yet. It has been accepted though. So it's, here you can see the combination of 3 different probes, BAO, DES data, Quasar plus, Pantheon again, and what is interesting is that when you start to include models that have more flexibility, like the interacting dark sector, these actually, we find positive alpha following this, the relation between pressure and density, and let's say, more consistent value was usually observed of the dark matter values that are shown here. We continue to investigate these, the sample of quasars, like fitting the Hubble diagram through different cosmological models, but now we are asking ourselves if there is any systematic effect that is affecting our results. So we do see a deviation from the expectation what is going on. So we try to redo the cosmological analysis over and over, trying to select subsamples in a way that can show us whether there is any systematic in the data set. And regardless the selection that we tried, we always see, these deviations. So here is again WA, W0. This is what we observed with quasars and the other probes, and this is what the CMB plus BAO and weak length predict. So, and we have consistency on our results regardless different approaches. Taking out the low redshift quasars, selecting by photon index. The photon index is the slope of the X-ray spectra, but we do observe the consistent results. So what I really would like is to have an independent test of this result that requires observational standard candidates at higher redshift. The other standard candidates at higher redshift that I'm aware of, gamma ray burst. But again, this is something that when gamma ray burst will be more the sample will be much higher, then we can try to compare these results with this sample. But what I'm looking really forward is future observation, if possible, of type 1a supernova ratio higher than 1.5, because already at that redshift, we do see a slightly deviation from the ΛCDM model. So that will be a really important test. I can proceed showing you what we obtained by investigating different cosmological models, but I think what is most important is to test whether the sample is affected by any systematic or bias. So are we selecting particular kind of quasars? Our assumption, like our working assumption, is that our selection criteria are tailored to select normal, blue, unobscured type 1 AGN. Okay, so is our selection criteria actually not fulfilling this requirement? So we did a series of tests, try to investigate the reliability of the technique. And I'm gonna go through them just to show you that we try to do our best to take into account all possible sources of bias and systematics. So we start by looking at the sample selection at redshift higher than 2.5, and why we did that, this was actually the most obvious things to do, because this is where we do see the deviation to appear. So this was done on all the high redshift sources that are in the sample that I've just shown before. We did a one-to-one analysis. The numbers were such that this was actually possible. And by doing actually these, so by doing a careful analysis one by one, which is just doable for subsample of sources, we do observe that the dispersion on the relation actually narrows down. When you stack the data both at X-ray and optical wavelength, and you compare the data, the composite with what you would expect, a much lower redshift from other sample of quasar, like for instance, the red line here is not a fit to the data. This is actually a template of quasars at redshift lower than 2 that has been published in 2001, and it is perfectly matching what we do observe a higher redshift. So really type 1 unobscured quasars, this is what we are looking at. So nothing weird on the sources that we are using for cosmology. And the same goes for the X-rays. So these we also test for the intrinsic contamination of host galaxy or extinction, because dust was one of our worries, and so we ask ourselves whether there is a differential reddening that explains why we do observe this flattening of the Hubble diagram, but the reddening that is required in order to put back the data on top of the lambda CDM prediction are just too high at those redshift. That this would require intrinsic luminosities well below 10 to the 49 x per second, which are unrealistic and never observed. We proceed also doing further tests on the data by fitting them, checking for, again, absorption, and we do see consistency. So we do actually, our selection criteria do actually pick sources that have low intrinsic reddening. For the low redshift, lower than 0.6, we do not correct for host galaxies, so everyone that wants to use the sample, which is actually publicly available, should avoid using quasar at redshift 0.7. This is the lower cut, unless you correct for host galaxy. So I want to move forward with the test of indicators, but I think I'm running out of time, so I want to show the last work that we have been doing, because of course a criticism has been raised on the technique, which is good. I mean, this forces us to look a little bit deeper, and so we published very recently this year a work where we address this criticism, and I'm going to just show you 2 plots from this paper. We do check whether the slope of the relation is consistent across the redshift range for which we can actually probe it, and this is well consistent from 0.6 from low redshift up until 3.5. This is just one example of the relation that we do across the entire redshift range. So there is no redshift evolution of the slope of the relation, and there is no redshift evolution of the intercept, the beta of the relation. And this is shown not directly, because of course the intercept of the relation has the luminosity distance in place, but you can see that there is a perfect match in the overlapping range with Pantheon plus type 1a supernovae in the Hubble diagram. So there is no reason to believe from this and from observational considerations that we are doing something or selecting some weird quasars in our sample. So having that being said, what is the future of the Hubble diagram? Because we have been working on this, and we want to increase the sample and keeping, of course, systematic biases under control. So there are 2 main surveys that we are actually planning to work with. One is we are currently working on is a sample of eROSITA sources. eROSITA is a quite shallow X-ray survey, but it's all sky. But being shallow means that we can look at quasars that are a low redshift. This is actually really good because these enable us to test the cross-calibration with hypernet supernova, which is used for the to actually determine the intrinsic distance modulus, so the cross-calibrated modulus of quasars. And so this is a work that we are doing right now, and we are actually working on high redshift quasars. Now Euclid was just launched, and we are waiting for the high redshift quasars to be discovered. And this is the other side of the Hubble diagram that we want to sample more. So 30 quasar redshift higher than 8 are expected, which is a really, really nice number if you want to put it in the Hubble diagram where the sample is sparse. Okay, so I'm done. So here my take-home message is, of course, we need to reduce the dispersion of the quasar Hubble diagram further, but I believe that we didn't really like a thorough work in order to select quasars for cosmological purposes. More can be done, and we are working on a new quasar sample for cosmology at the moment, so stay tuned. Okay.
Thank you very much, Elisabeta, for your talk. Questions, please?
Thank you, Beta, for your talk. Actually, I would like to mention about number one of your conclusion that we found in a series of papers led by me in 2023, 2024 ABC, that there is actually evolution of the correlation of the luminosity accent UV, but this is not an issue for cosmology, so because when you correct for this redshift evolution effect together with the cosmological parameters, you still find the intrinsic slope of the correlation. But I think it would be good to acknowledge the existence of this evolution and how this is corrected through the Efron and Petrosian method, and to change contemporaneously the parameter of cosmology with this evolution, as we did in series of paper.
Okay, so I'm very well aware about this Efron and Petrosian technique, and the reason why I didn't study it is because I am more observationally driven approach. So what we did in order to check whether the slope and the intercept actually evolve with redshift, which they don't, for at least within the redshift range that we can probe between low redshift and redshift 3, is purely observationally driven. So from our investigation of the parameter space of the correlation parameters, we have not found any reason to believe that this evolution actually exists. However, the approach that you were mentioning are actually assuming a model, a relation, a parametrization of the parameters. Whether this is what nature decided, that the slope and the beta are actually like evolving, using to evolve with redshift, this is something that I have not explored yet, but this is just a different approach.
Actually, there is a paper from Sikora of 1990 that refers to the evolution in physics of the quasars for this, so you can check
Depends
that,
on
and you can refer to the physics, not only on the phenomenology. But of course, I don't want to, keep discussing. We can discuss in the coffee break. Yes.
Any further question?
Hi there. Can you go back to that plot you had from the paper that was a reply to a criticism?
Yeah, I mean, in that paper, we actually did more than that. We did simulations, mock samples to check whether this or this one.
Yes.
Yeah.
Can you explain what's the middle panel?
Yeah, I haven't discussed about this. I'm sorry. I was just focusing on the top part. So the middle one is the dispersion. How the dispersion. So this delta that you see here is how the dispersion in each pin varies in redshift, and the blue dots. While this different shade of blue, it is actually checking that in this bin, we are always above this threshold. So this is a sanity check that we always do when you bin the data. You never want to have a dispersion that is actually consistent with the observed scatter, taking account errors, okay? So you are statistically significant. While the bottom part is the intercept in the FX FUV. And this is when you see the trend with redshift. This is perfectly fine because this is actually the Hubble diagram.
Okay.
Beta is the luminosity distance in a sense, beta hat.
In the middle panel, the darker blue with the error bars, what's that showing?
These error bars, you mean?
Yes.
These are the uncertainties on the intrinsic dispersion of the relation that we estimated through an MC approach.
Okay.
So
and the fact that it's kind of like the points are kind of going down, that's not an issue.
You have to look at the scale. This is not actually a statistical significant. And then the samples start to become a little bit sparse at redshift 3, but it's not a statistical trend.
Okay.
Yeah, it's very well consistent with no trend at all within uncertainties, of course.
Mm-hmm. Okay, thank you.
Thank you very much once again, Beta. And